Hello and welcome guys to my YouTube channel. In this video we will be covering real life scenarios about upper and lower bounds and the operations between them. Okay, so let's take a look at the first example. Figure 1 shows a rectangle. Given that the length and the width are equal to 7 centimeter and 4 centimeter respectively. So this right here, this is the length and this is the width. Both correct to the nearest centimeter. Part A asks us to find the maximum possible area of the rectangle. Okay, so we want the area max, or the upper bound of the area. And now we know that the area of a rectangle is length times width. Now, both of the length and the width are correct to the nearest centimeter, which means they have an upper and a lower bound, both of them. So now if we take a look here, we want the upper bound for the area, and we have length times width, so multiplication. So to achieve an upper bound from a multiplication, we would want the left-hand side to be upper bound and the right-hand side to be upper bound as well. This was covered, the operations between lower and upper bounds were covered extensively in the last video. So if you didn't watch it, I would highly recommend you go and watch it. Now, so we want the upper bound for the length and the upper bound for the width. Let's go ahead and find those. So we know that the length is equal to 7 centimeters, and this is correct to the nearest centimeter. So the unit of round is 1, because it's the nearest whole number. So divided by 2, this gives us 0.5, and this is our error. So now the length, the upper bound of the length is 7.5. We got this by adding 7 plus the error. Now as for the width is 4 centimeter, also to the nearest centimeter. So our unit of round is 1. Dividing this by 2, it gives us 0.5. So width, upper bound is basically 4.5. So now we can go ahead and substitute. So 7.5 times 4.5, okay? And you can just plug this on the calculator and we get 33.75 centimeters squared, okay? Rounded to 3 significant figures, this is 33.8. So this is the answer. This is the maximum area of the rectangle, the maximum possible. Okay, part B. Find the minimum possible area of the rectangle. So we want the A min for a minimum, or the lower bound of A. Now the rule doesn't change, it's still length times width. However, this time you want the minimum of the lower bound. Again, this is a multiplication. To achieve the lower bound of a multiplication, we'd want the lower bound over here and the lower bound over here. So now I can go ahead and say that now the lower bound for the length, we didn't find it, but we can just find it easily right here. So length, lower bound for length is going to be 7 minus the error. So it's 6.5. And the lower bound for the width is also going to be 4 minus 0.5, which is 3.5. So now we have all of the upper and lower bounds for both variables ready for use. Now the lower bound for the length is 6.5 and the lower bound for the width is 3.5. And now we can go ahead and substitute this on the calculator. And we get 22.75. Now rounding this to 3 significant figures, it's 22.8 centimeters squared. Okay. So as you can see, in part A, we found the maximum area, which is 33.8, and in part B, we found the minimum area, it's 22.8. There's quite a difference, and that's how much it matters that since they're to the nearest centimeter, the combination of upper and lower bounds can give you the minimum and the maximum. Now, let's take a look at C. C is asking us to find the maximum perimeter of the rectangle. Now, the perimeter of a rectangle is 2 times the length plus width. Okay, these rules are rules that you should already know by now. If you don't know them, well, now you do. Okay, so now for the perimeter, we want the maximum, or basically the upper bound. Now, we have a length plus the width, and then it gets timed by 2. Now, you need to understand, don't ever grab this 2 and find an upper bound or a lower bound for it. This is a constant that does not change. Okay? Nothing you can do about the 2. It's not rounded, it's constant. Now, the length and the width, they both have an upper and a lower bound, and we want to get the maximum possible. So we want the upper bound for the length plus width, which means we would want the upper bound for the length and the upper bound for the width, because this is an addition operation. So we can just go ahead and write that 2 multiplied by the upper bound for the length is 7.5. We already found it. And the upper bound for the width is 4.5. We're going to go ahead and plug this on the calculator. We get 24 centimeters. This is the perimeter. Finally, part D, the minimum perimeter of the rectangle. So perimeter is equal to, again, 2 times length plus width. But this time we want the minimum for P, or the lower bound. So again, we have the length plus the width times 2. We want the minimum of length plus width. This is an addition operation. To achieve the minimum of 2 variables being added together, we take the lower bound for this and the lower bound for the other variable. So it's going to be 2 times 6.5 plus 3.5. And we're going to go ahead and plug those numbers on the calculator. And we get 20 centimeter. Okay, so this is the minimum possible value of the perimeter. Moving on to the next example. Okay, so to the nearest dollar, Sarah has $25. To the nearest 50 cents, Michael has 18.5 cents, 0.50. What is the maximum possible total amount of money they could have together? Okay, so let's take a, so we have Sarah with $25 to the nearest dollar. Okay. And we have Michael with $18.5 to the nearest 50 cents. I forgot to write the 1 here, okay? Now, we're being asked, what is the maximum possible total amount of money they could have together? Okay, so if you remember, when you have the same unit and it's being rounded, so we have $25 being rounded to the nearest dollar, then the unit of round is just 1. Whereas for Michael, we don't have the same unit. So either these dollars have to turn into cents, or these cents have to turn into dollars. Okay. Now, while we're at it, we're being asked for the total amount of money. The total amount of money will be basically amount is equal to Sarah's money plus Michael's money. Okay. Now, we want to know the maximum possible amount of money, or the upper bound that they can have, which means we have an addition. So the upper bound for this operation would be the upper bound for Sarah's money and the upper bound for Michael's money. So let's go ahead and find the upper bound for Sarah and the upper bound for Michael. For Sarah, it's quite easy. We know that she has $25 and that the unit of round is 1. Dividing this by 2 gives us 0.5. And so Sarah upper bound is 25.5. Okay, this is the maximum she can potentially have. Okay. Now for Michael, we know he has $18.5, yes, but the unit of round is 50 cents. Now, to change the cents to a dollar, we know that a dollar has 100 cents, so we divide by 100, okay? So 50, and we're gonna go ahead and divide that by 100. It would give you 0.5, okay? Now, this is 0.5 dollars. So now we know that Michael has $18.5 to the nearest $0.5. So we can go ahead and divide 0.5 divided by 2, which gives us 0.25, okay? And so the upper bound for Michael, sorry, I wrote Sarah. The upper bound for Michael's money will be basically 18.5 plus 0.25, your amount plus the error. This is the error. And we get 18.75. Okay? So now the maximum that they can have together is upper bound for Sarah, which is 25.5, plus the upper bound for Michael, which is 18.75. So you can go ahead and plug these numbers on the calculator, and we get 44.25. Okay? Of course, this is in dollars. They must be in the same unit before you add them. Okay, moving on. Third example. A car travels 245 kilometers, correct to the nearest 5 kilometer. The journey takes 3.8 hours, correct to 1 decimal place. Find the maximum possible average speed of the car. Now, the average speed is equal to the total distance over the total time, okay? Now, of course, this rule you should be familiar of it through physics, or you can just learn it now. Speed is equal to distance over time, but the average speed is total distance over total time. So now we know that the car traveled a distance of 245 kilometers to the nearest 5 kilometers. Okay. And the time that the car took is 3.8 hours, correct to 1 decimal place. Now, we want the maximum possible average speed. The average speed, you want the maximum of it, so this right here, we want the max. So we would want the upper bound for the speed. And we have a division right here. So to get the upper bound from the division, we would want the upper bound from the top and the lower bound from the bottom, the denominator, and the top part is called the numerator and the bottom part is the denominator, okay? So let's find the upper bound for the distance. So the distance is 245 and the unit of round is 5. So just going to go ahead and divide this by 2 and we get 2.5. So the upper bound for the distance is the addition of 245 plus 2.5. So 247.5. Now, as for the time we want the lower bound, we know it's being rounded to 1 decimal place, okay? This right here, this is the first decimal place, so replace that by 1, everything else turns to a 0, and divide this by 2, we get 0.05. So time, lower bound, is basically 3.8 minus the error, which gives us 3.75 hours, okay? So now, let me take this on over here. Okay, so the total distance is going to be, the upper bound, sorry, for the total distance is 247.5 divided by the total time, which is 3.75. And we're going to go ahead and plug those numbers on our calculator. And we get 66. Of course, the unit here is kilometers per hour, okay? Because the time is in hour and the distance is in kilometers. Moving on to the final example. Emily's apple farm produces an average of 150 kilograms of apples per day. This is rounded to the nearest 5 kilograms over a period of 45 days. She packages the apples into crates, each holding 12 kilograms of apples, rounded to the nearest kilogram. Calculate the maximum and minimum number of crates Emily will be able to fill. Okay, so let's understand the scenario. So basically, Emily produces 150 kilograms of apples. This is per day. And this is rounded to the nearest 5 kilograms. Since it's rounded, that means the number over here, the 150, definitely has an upper bound and a lower bound, okay? And this is done over a period of 45 days. And each day, what she does basically is that she empties those apples into crates. And each crate holds 12 kilogram. That's 12 kilogram per crate, okay? And this is to the nearest kilogram, right? So since it's also rounded to the nearest kilogram, that means the amount that each crate holds has an upper bound and a lower bound, okay? Now, we want the maximum and the minimum number of crates Emily will be able to fill. Now, to find that out, let's firstly find how am I even going to find the number Emily will be able to fill. Now, in order to find the number of crates, we would have to divide the amount of apples, so we'll call this the amount, and divide that by the weight that each crate holds, which is 12. So by the weight, okay? And then we will multiply the result by 45. This right here will give us the amount, the crates per day. And then we multiply by 45 days, we will get the amount of crates over the period of 45 days, okay? Now, so here's the thing. The reason we're using variables here and not just 150 and 5 is because we have an upper and a lower bound for the amount of apples, and we have an upper and lower bound for the weight of each crate, okay? So now we know that at first we want the max number of crates or the upper bound. And then in this case, it's just a simple division, okay? So if you want the upper bound for the division, you would want the upper bound for the amount and the lower bound for the weight of each crate. And it makes sense. You want the highest possible amount I can have, so the upper bound, and you want the crates to weigh the least possible amount, which is the lower bound, okay? So I'm going to go ahead and find the upper bound and the lower bound for each of those. So let's find it over here. So for the apples, we're talking about 150 kilograms to the nearest 5 kilograms. It's the same unit, so I'm just going to go ahead and divide this by 2, and we get 2.5. This is supposed to be 5. And so the upper bound for the amount of apples is 152.5. As for the crates. Each crate weighs 12 kilograms to the nearest 1 kilogram. So the unit of round is 1, nearest whole number. And this gives us 0.5. And so the crate, the upper bound for the weight of the crate is 12.5. But sorry, we don't even want the upper bound right now. We want the lower bound, which is 11.5, okay? So now, to get the maximum number of crates, it's going to be 152.5 divided by the weight, the lower bound for the weight, which is 11.5, and multiplied by 45 days. So the maximum is equal to, and you can go ahead and plug your numbers on the calculator. And we get 596.739 and so on. Now, the final answer is 596. Now notice that I did not round up, even though technically the 6 should round up because we have a 7 on the right. But the reason for that is we're being asked for the number of crates, okay? So based on this information right now, the crates that I filled were 596. The next crate was only filled like 0.7. So it wouldn't make sense to round up. I didn't fill 597. I only filled 596. So this is my final answer for the maximum. Now for the minimum number of crates, or the lower bound, it's the same rule. There is no difference in the rule. However, this time you would want the lower bound for the amount and the upper bound for the weight. And it makes sense. You want the minimum number of crates. So you want to have the minimum amount of apples, which is the lower bound for it. And you want to have dividing it by the maximum weight of the crates, which is upper bound. Okay? So now we want the lower bound for the amount. And we already found the upper bound over here, so we're just going to find the lower bound right there. The lower bound will be 150 minus the error. Okay? And that will give you basically 147.5, okay? Now, also, we want to find the upper bound for the crate now. So the upper bound over here is going to be the 12 plus the 0.5, which is the error, which gives me 12.5, okay? So those are going to be the numbers that we're going to be using. 147.5 divided by the upper bound for the weight, 12.5, multiplied by 45. So we get that the minimum is equal to, and we'll plug those numbers on the calculator. And we actually get 531 exactly. So this is the minimum number of crates. As you can see, there is a big difference. Okay, so hopefully those examples were clear. Now let's take a look at some exercises to make sure that you understand. You should pause the video and try to solve each of the exercises on your own first. Alright, so the area of rectangle is calculated using the formula area is equal to length times width, where the length is 15.2 and the width is 7.3. Both correct to 1 decimal place. Calculate the upper bound for the area. Okay, so the upper bound is equal to the length times the width, and we want the upper bound of the area, or the maximum. This is a multiplication, so if you want the upper bound, you would want the upper bound for this, and the upper bound for the width. Now let's find the upper bound for both. Now we know that the length is equal to 15.2, and this is correct to 1 decimal place, which means this is the first decimal place right here. So 0.1. Dividing this by 2 gives us 0.05. And so my length upper bound is addition of 15.2 plus the error, which gives you 15.25. Now, The width is equal to 7.3, also correct to 1 decimal place. So this is 0.1 right here. Dividing this by 2 gives us 0.05. And so the width, the upper bound for the width is basically 7.35. We got this by adding the value of the width plus the error. So now the upper bound for the area is equal to my length, which is 15.25, times my width, which is 7.35. And you can go ahead and plug this on the calculator. And you will get 112.0875. Now I will be rounding this to 3 significant figures, so 112. Of course, this is measured in centimeters squared because it's an area. Moving on to the next question. A student measures the resistance R of a circuit using R is equal to V over I. Of course, this is not a rule you should know in the exam. This is given to you in the question. Where the voltage V is equal to 12.5 and current I is equal to 2.3 amperes. Both correct to 1 decimal place. Determine the upper bound for the resistance. So we want the upper bound for the resistance. So let's write the formula firstly. So R is equal to V over I. And we want the upper bound for R, okay? So that means this is division. So we would want the upper bound for the top and the lower bound for the denominator. Now let's go ahead and find each of those. So we know that V, the voltage, is equal to 12.5. And it's correct to 1 decimal place. Both the voltage and the current are correct to 1 decimal place. So this will be 0.1. Dividing this by 2 will give us 0.05, all right? So the upper bound for the voltage is going to be the addition of 12.5 plus the error, which gives you 12.55. Now, as for the current, I is equal to 2.3, also correct to 1 decimal place. So this right here is a 1, 0.1. Dividing this by 2 gives you also 0.05. So the lower bound for the current is the subtraction 2.3 minus the error, which is 2.25. And I'm going to go ahead and plug in our variables. So the upper bound for the resistance is 12.55 divided by 2.25. And you can go ahead and plug this on the calculator. And we get 5.57 recurring. If I want to round this to 3 significant figures, it's going to be 5.58. This is the resistance, okay? Okay, third question. A bakery produces 250 loaves of bread each day. Correct to the nearest 10 loaves. Okay, so we're producing 250, correct to the nearest 10. That means this 250 has an upper bound and a lower bound. And this goes on for 30 days. Each loaf is sliced into 16 pieces. Calculate the minimum number for the total number of slices the bakery will produce over 30 days. Okay, so we know that each loaf is sliced into 16 pieces. So now if we want to know, first let's start. So we have 250 loaves, okay? And this is to the nearest 10 loaves. And we're doing this for 30 days. And what we're doing is we're slicing each loaf into 16 pieces, okay? So in order to know the number of pieces, Well, we know that each loaf will become 16, correct? So it's going to be, the number of pieces is going to be the number of loaves multiplied by 16. Every single loaf will become basically 16 pieces. So we'll multiply. If you had 10 loaves, each of them will become 16 pieces. You'll have 160 pieces. We found out by multiplying 10 by 16. Okay. Now, the question is asking for the minimum number of slices or pieces. It's the same thing. The bakery will produce over 30 days. So the number of pieces or slices, we want the minimum or the lower bound, really. Okay. So the good thing here is that we only have one number that has an upper and lower bound, which is this, the number of loaves. So if I want to know if I want to have the lower bound for the number of slices, this is a multiplication. So simply we want the lower bound for the number of loaves. Okay. But this 16 over here doesn't have an upper or lower bound. They never mentioned any rounding for it. They just said 16 pieces. So now let's find the lower bound for the number of loaves. So we have 250 loaves to the nearest 10 loaves. So we'll divide 10 by 2. We get 5. And so the lower bound is basically 250 minus 5, which is 245. So I can go ahead and put 245 right here and multiply this by 16. And plugging this on the calculator gives us 3,920. Okay. So this right here is the minimum slices per day. Okay, so be careful. We're still only doing this per day, okay? Because per day, the minimum number of loaves I produce, which is the lower bound, is 245, multiplied by each loaf becoming 16 pieces or 16 slices. Now, if I want to know the minimum overall, I will multiply 3,920 pieces per day multiplied by the period of 30 days. And so we get that the minimum is equal to 117,600 slices. Okay. Okay, so final exercise. The length of a piece of fabric is 20 meters. Correct to the nearest meter. So again, since it's correct to the nearest meter, this has an upper and a lower bound. The piece of fabric is cut into sections of equal length of 1.5 meters to the nearest decimal place. So this right here also has an upper and a lower bound. Calculate the maximum number of sections. Okay. So if you have a length of fabric that is 20 meters long and you're cutting it into sections 1.5 meters each, let's figure out a rule to know the number of sections. So the number of sections. So we're basically dividing 20 by 1.5, another 1.5, and so on. So this will be a division operation of the length of the fabric and dividing this by the length of the section. Okay, so this is the rule. Now through this rule, we're going to find the maximum number of sections. So we want the maximum for the number of section or the upper bound. Okay. Now, don't forget, the length of the fabric was rounded to the nearest meter, and the length of the section was rounded to the nearest 1.5 meters. So both of them have upper and lower bounds. Now we want the upper bound for the number of section, and this is a division operation. So we'd want the upper bound for this one and the lower bound for this. Okay. Now let's go ahead and find the upper bound of the length of fabric. So we know it's 20 meters. And this is correct to the nearest 1 meter. Okay. So we'll divide this by 2 and it gives us 0.5. And so the upper bound is 20.5. I'm gonna already go ahead and put this over here. Now, as for the sections, they are 1.5 meters, correct to the nearest decimal place, as you can see here. So the unit of round is 0.1. And dividing this by 2 gives us 0.05. And we want the lower bound, so we're going to do 1.5 minus 0.05. And so the lower bound is 1.45. And I'm going to go ahead and plug it over here. And now we're going to input those numbers on the calculator. And we get 14.137 and so on. So the final answer, the maximum you can have, is actually 14. Okay, 14 sections. And just a heads up, even if this was 14.9 or 0.99 and so on, you would never make it 15, okay? Because you only have 14 whole sections. So we don't round this up. We simply take the integer value, which is the whole number, which is the 14. Okay, so that's it for upper and lower bounds. Thank you for watching.